Oh, very good. Welcome back to this last part of the lecture. Uh, the we in the previous lectures we have been designing probability theory as a tool to handle reasoning with incomplete information, and the way we did it was we decided we wanted to describe degrees of rational belief, and we said, well, degrees of rational belief, if they're to be useful at all, they ought to satisfy certain basic desirability features, and if we try to implement them mathematically, we're going to get a mathematical framework. It turned out to be the case that the mathematical framework is essentially unique. You can always regraduate these probabilities and obtain a mathematical framework that's more complicated, but effectively it's equivalent to it, right? It's just a change of variables. So what I would like to do now is dwell a little bit more on this, because there are other approaches to probability that have to do with figuring out the number of successful outcomes in a large number of trials, or assigning probabilities to variables that are said to be random. So how does the degree of belief approach to probability? How is it related to these other approaches, frequentism or the probability of random variables? Very good. We're going to deal with frequency, maybe in frequentist approaches, and see how our approach here incorporates frequencies in large number of trials in a very natural way as a special case. This is more general because it applies to also a finite number of trials, or even to just one trial. So we're going to see later how that comes about. But here I wanted to talk a little bit more about randomness. Where are the random variables here? Aren't probabilities supposed to be tools to describe randomness in the universe? Well, I would like to claim from the start that randomness is a pretty tricky concept. If I were to flip a coin, here I'm flipping a coin, and the coin goes like that and lands, you could say, okay, it landed there. I have no idea. It could have gone one way, it could have gone the other. This is a random effect. This is random. On the other hand, if you were sufficiently clever and you were to give the coin a certain initial angular velocity, and you throw it up with a certain speed, and you knew all those details, it's fairly clear that you would be able to compute how it lands. In fact, magicians can do that pretty well. They train themselves to throw it in such a way that it goes 3 turns and lands, 3 turns and lands, 3 turns and lands. So for them, it's not random at all. So what is randomness? When it happens that there is information out there that's sufficient, that determines what the outcome is, but that it is sufficiently complicated that you cannot keep track of it, then you call that random. The result of it being sufficiently complicated is that you just do not know it. And that's why probabilities are useful for random phenomena. It's because there might be information out there or not. You do not know it, and so you are forced to use probability theory to analyze this phenomenon. Here, let me give you the same example again. I flip my coin and say, okay, yes, that's random. Let us assign probabilities to this. It could have been heads. It could have been tails. I have no way to prefer one over the other. Therefore, I assign probability 1/2. That's kind of a clever thing to do. It's called the principle of insufficient reason. And if you think about it, principles are tricky because many times they don't work. But in any case, what we have here is a situation of symmetry. I am indifferent about heads or tails. There is a symmetry in my ignorance. I do not know which one it is, and therefore, if I'm going to represent that symmetry, I'm going to assign probability 1/2 to each one of them. As a side, nice, interesting philosophical remarks, the questions will begin to arise. Could it possibly be the case that every time that we use symmetry in physics is somehow connected to our state of information or a state of ignorance about the system, is such that that is what is symmetric? Not necessarily the system itself, but our state of information might be symmetric, and that's why we introduce symmetries immediately. Keep it in your back of your mind. Interesting idea. In any case, here we have our coin. There is our coin, 50-50, right? Now, I look at it. For me, it's not 50-50. For me, it's 1 and 0. For you, it's still 50-50. You have not looked at it. So one of the things that this starts indicating is that two different rational agents can assign different probabilities, no problem, whenever they are in different states of information. The probability is not a feature of the system, it is a feature of your state of information. For me, it's 1. For you, it's 50-50. Here's another one. I'm going to toss the coin, but I'm not going to toss it like that. I'm going to put it there and cover it. Now, I put it there. Once again, you can see that there was absolutely nothing random about the way I placed it there. I know, for me, the state of this coin is going to be 100% one or 0% the other, right? I'm certain what it is. Nothing random there. But for you, it's still 50-50 because you do not know. So this once again indicates that the fact that you have probabilities has nothing to do with randomness. It has to do with lack of information. If it so happens that the phenomenon is very complicated, well then, if it is complicated, that explains why you don't have the information and you call that random. But okay, long story short, randomness is included in our framework of inference trivially. You do not need to talk about random variables, and from now on, I will refrain from doing so. Very good. Let me now talk about a little bit more about names. I should go here and there. And now that we're here, let's talk about, having talked about randomness as being a special case, we're going to talk about certain, names, definitions that are useful. Independent events, independence. Two propositions or two events are independent when you want to figure out the probability of one, it does not matter whether you know the other or not. So when the probability of A is the same as the probability of A given B, knowing B didn't matter, right? So then we say that that A and B are independent. Notice that when we have the probability now of A and B, we can write this as, use the product rule, probability of the first, probability of the second given the first. If they are independent, it doesn't matter whether I know the second one or not. So for independent events, you just get a product of the two. So this is all for independent events. Clearly, P of A and B is the same as B and A. That's what I used here already. And you can see that these two are perfectly symmetric. And what that means is that if A is independent of B, then B is independent of A. All right, that's the first term to recognize as being important. We are also going to talk about events that are mutually exclusive. Mutually exclusive events are events that cannot be true simultaneously. Together they cannot be true. So for example, A and B are mutually exclusive when A, B is false, which means that A and B is 0. When they're mutually exclusive, they cannot happen together. And when that happens, so this is the first important little formula here. So this is one. It's just boxing. This is the definition. That's the conclusion. This is the definition, essentially. And when this happens, the probability of A or B is just the probability of one plus the probability of the other, because minus P, A, and B is going to be 0. So that's the definition of mutually exclusive events. Typically, the situation is that if you're going to toss a coin, it cannot come out heads and tails. You toss a die, it cannot get 1 and 2 at the same time. You get one or you get the other. If you get one, you do not get the other. So that's what mutual exclusivity is also all about. Let me see. The fact that you get this sum rule here means that if you have many, A1, A2, A3, and so on, AN are mutually, AN are mutually exclusive, then the probability of A1 or A2 or AN, that's going to be, well, how do you do this? Well, the way you do this is to say, well, if these are mutually exclusive, this piece is mutually exclusive from that, so it's going to be the sum of the first and the second. But then the second, you can separate this into this guy being mutually exclusive from the rest, and so on. So this is just going to be the sum of all the possibilities of those probabilities. So when things are mutually exclusive, the probabilities of these junctions add. What else can we say about these guys here? Yes, a set of events or a set of propositions, A1, AN, is exhaustive when they cover all possible outcomes. So, for example, for a coin, heads or tails, those are the only two possibilities. No such thing as the coin coming out on an edge, right? For a die, 1, 2, 3, 4, 5, 6, those are all possibilities. When that happens, then what you have is that A1 or A2 or and so on or AN happens to be true. It has to be one of those. It's the statement that lies at the very top of the lattice of propositions. And when that is the case, then this means that the probability of A1 or A2 or AN is equal to 1. Finally, if the set of events is mutually exclusive and exhaustive, only one of them can be true, mutually exclusive. If one is true, all the others are false. If A1 through AN are mutually exclusive and exhaustive, then the probability of one or the other is just going to be, well, we look up the formula up here, the sum of all the probabilities. And on the other hand, we look at this expression here, we get 1, and this is what we mean by saying that probabilities are normalized. So we have a bunch of words there. Once you get used to these words, mutually exclusive, exhaustive, independent, it's trivial. But at some point, in the beginning, sometimes it's a little bit nasty to try to get used to them. Let me address one final issue here that's really important, and then I'll give you a physics example. Marginalization. Remember when we drew that lattice of propositions, and I said, look, here you have the whole universe of this course. You have the whole set of propositions that you can that you can form by using and or. So all of these propositions are sort of connected to each other by ands and ors. Then we want to sprinkle this lattice. We want to put probabilities on this lattice. And what we find is that once you set the probabilities of some of them, the probabilities of all the others are determined. This is the real value or the real importance of the sum and the product rules. You fix once. If you want to be consistent, the others are rigidly determined. Very good. It may be the case that you're talking about two different systems that are brought together, or two different sets of variables. So suppose that you have two sets of variables, two or more. AI and BJ. And suppose that the probability of some of these guys of PAI and BJ is known. So suppose that the probability for some of these are the joint probabilities for some variables and some others. Suppose that these are knowns. What can we say about the probability of the A's and the probability of the B's separately? Well, let me assume that these variables are mutually exclusive and exhaustive, that the BJ's are mutually exclusive and exhaustive. Now, it may seem that these are special cases, mutually exclusive and exhaustive. Of course they are, but they're very important special cases, and we're going to see that most of the time you're dealing with these situations. So suppose that the BJ's are mutually exclusive and exhaustive. Then consider the following. Suppose that you have the probability of AI BJ and I'm going to sum over all j's. This is a product. So I can use the product rule, do the probability of the first, and then do the probability of the second given the first. Very good. Notice that the summation is over j. This guy does not have a j. So this guy is just a constant in the summation. I can pull it out. Sorry, mistake here. AI. Mistake there. Sum over j p bj ai. Very good. If these b's are mutually exclusive and exhaustive, then what we have here is a sum of probabilities of the bj's over all possible situations, which is exactly the kind of thing we have down there. So then this is equal to 1. Conclusion, when you have propositions that are mutually exclusive and exhaustive, and you sum over a bunch of them, you obtain the probability for the others. So this procedure, which is actually really important, we're going to use it in quantum mechanics once we get there, okay, to derive quantum mechanics. This procedure is called marginalization. And let me give you two examples. One of them will make clear why it's called marginalization. Suppose that suppose that you have this is an example taken from, say, medicine. You have patients that have either have cancer and or diabetes. So these guys are really screwed up. And we're going to call this C, and we're going to call that D. So we can actually try to write out what the probabilities are in a 2x2 table. Doctors and people who do statistics for doctors are always talking about 2x2 tables, because typically you have the guy who's sick or not sick. So the way we do this is when I say either the patients have cancer or they do not, and they have diabetes or they do not. So clearly you can see now that these cancer and not cancer, these are mutually exclusive. If you have it, you have it. If you don't, you don't. Right? And also exhaustive. It combines all possibilities. And here we're going to have the probability of C and D. Here we have the probability of not C and D. Probability of C and, not D. Probability of not C and not D. Very good. Suppose I were to ask now, what is the probability of having diabetes? The way to do the probability for diabetes is going to be by adding over C and C tilde. So it's going to be by this formula we just wrote down here. We are going to add over all values of the mutually exclusive and exhaustive variables. So this is going to be the probability of CD plus C not, D. And similarly here we write the probability of not diabetes by saying probability of cancer and not diabetes plus the probability of not cancer and not diabetes, right? You do it by adding in this direction. Okay, so that's obvious, right? Okay, now the only purpose for my calling your attention to this example is that typically people would sum across a row and write it in the margin. So that's why the procedure is called marginalization. And you can either write it in the right margin or you can write it in the lower margin and write that the probability of cancer is the probability of CV plus probability of CV. So that's where the word marginalization comes from. Not particularly deep. But in physics, we do marginalizations all the time, but we never write it in the margin. So it's always has always been a big question of mine. Where does this word come from? Why are statisticians doing this to me? Let me do another example. This is going to be an interesting example because it's a little bit more physical. Suppose you have a bunch of particles and you're going to talk about the probability of positions and probability of momentum. Maybe I should use a capital P here. Positions and momentum. This really means the set of all positions, and this means the set of all momenta. And we're going to write that probability as being some normalization constant. Then the exponential. This system is a system is in thermal equilibrium, and so here we're going to write out minus beta, where beta is 1 over kT. So this is a system in thermal equilibrium. System in thermal equilibrium is a system that has a temperature. We're gonna kill this problem to death later, but anyway, here we're going to add all the probabilities, all the energies, p squared over 2m kinetic energy, plus some potential. X stands for all the position variables. So here you have, you clearly see you have the energy. So that's the Gibbs or Boltzmann distribution for the probability of a system in thermal equilibrium. First thing, note, do you see from looking at this exponential here that the probability of X of positions and momenta factors into the probability of positions times the probability of momenta? Look, it's an exponential. This is a sum. The probability of positions has to go with the exponential of minus beta d, while the probability of momenta is going with minus beta, the sum of all the p's. In fact, when you look at the probability of momenta, this is a sum too. So all the kinetic energies of all the particles are also independent of each other. So, oops, let me see. Let's go back here. So positions. Okay, let me write it like this. Positions and momenta are independent of each other. And that comes from the structure of the Hamiltonian. The fact that the kinetic energy adds to the potential energy means that when you put them in an exponential, the exponential of A plus B is the exponential of A plus the exponential of B. It's a product. And if you look at here what result we have for independent variables, where are we? Here. A and B are independent when the probability of A and B, the joint probability, separates into the probability of the two. That's exactly what's going on here. So position and momentum are independent. Very interesting. Suppose that we were to ask for the kinetic energy, the mean kinetic energy. When we do the mean kinetic energy for one particle, we're going to do these things in detail later. But for one particle, each particle, the kinetic energy is independent of the other because this separates into its factors, right? So you can compute each one of them. And when you compute each one of them, what you find is that basically you do the average over the various momenta. The positions are normalized by themselves. So you integrate over position, that gives you 1, it disappears. Then you integrate over the remaining probability, this one here. For all the particles, it's just normalization, it disappears. And you end up with just an integral with a Gaussian, it's a square. And you do that, and you get something like 3/2 kT for each particle. Very nice. This is one of the definitions that people use when they introduce the notion of temperature. They tell you something along the lines of the temperature is a measure of the mean kinetic energy per particle, per degree of freedom, right? All of that, yeah, that's fine. There is no problem with that definition of temperature, except that it might be a little bit limited, because if temperature is something that has to do with kinetic energy, then how do you do the temperature of a gas of photons? There, it is not so obvious what the kinetic energy of a photon is going to be, and it's definitely not going to be quadratic in the momentum anyway. So this definition, while correct, in the particular case of distributions of this type, it's not sufficiently general to be useful. So we're going to have to come back to how to define temperature. So this may be used as a definition of temperature. Very nice. But I would like to make yet another remark here that might be interesting. You probably have heard of doing this definition of temperature when you're dealing with gases. But how about when you're dealing with liquids or solids? Note. What is the difference between a gas, an ideal gas, and a liquid or a solid? Well, in an ideal gas, you don't have a potential. The potential is not there. They don't interact. And so for an ideal gas, you actually just go and compute, and this is what you get for the temperature. But suppose I were to tell you that this is not an ideal gas. This has been compressed into being a liquid, so that there are potentials. The atoms are actually bumping on each other. Or you are in a crystal where the atoms are connected by bonds or something, so that you have a bunch of harmonic oscillators going on there. How does that affect the definition of temperature? Well, have you noticed how the V that was here when I computed the expected value of the kinetic energy, the V disappeared because the positions and the momenta are independent. So the potential dropped out. So this calculation, which tells you that the mean kinetic energy is 3/2 kT, is true for ideal gases and liquids, solids, and so on, as long as the position variables and the momenta are independent of each other, and that happens when you have the kinetic energy depending on momenta and the positions depending on the and the potential energy depending on position. This is always true. So to say that the temperature, this is a decent definition of temperature, is actually pretty decent. It doesn't work for photons, but it works for all sorts of matter, unless it gets relativistic, and then you end up just having photons again. So this is actually a pretty decent calculation. So independence matters a lot in physics. Here, let me note yet another thing. Suppose that the potentials, like this is like a gas. Okay, let's go back. Suppose that you have an ideal gas in an external gravity field. Suppose that you have that V is a position of, is a something that depends just on the height of the molecule. Pretty amazing, huh? What do you get then for the expected value of momentum, of a momentum? Well, you look at the probability up here. Well, first thing, the probability, the momentum, no, sorry, the potential energy, mgz, enters here. So we're still in this situation in which positions and momenta are independent. So it doesn't matter whether you're in a liquid or a gas or whatever. This drops out. It doesn't matter if you are in an external gravitational field. This drops out. So what is the expected value of momentum? You have your gas. The molecule can go just as the same probability going in one direction as going in the opposite direction, right? Positions do not matter. This is 0. How about the probability of p squared? That's not 0. P squared over 2m was 3/2 k2. So here we put the 2m, and here we put the 3/2 kt. So this is what p squared is. It's 3m kt. Very nice. But look at this result here. Wouldn't you expect that as particles climb, you have a gravitational field. If the particle is climbing, doesn't it slow down? So you would expect the kinetic energy of particles up here to be lower than the kinetic energy of the particles down there. And yet, this is independent of z. Question. What's going on here? Actually, it's very, it's the solution is kind of trivial. In a gravitational field, the particles that climb slow down. But if the particles didn't have that much of a speed to start with, they do not get up here, they fall. They never get up here. So the net result is that those particles that have low speeds never make it to be up here. It's only the ones with high speeds that make it to be up here. So that shifts the probability distribution towards higher energies. On the other hand, those guys with higher energy, by the time they get up there, they're going to have lower speeds. So the two effects, the slow particles do not make it up and the fast particles get slowed down, the two effects cancel out, and the net result is that this is independent of z. What does happen in a gravitational field is not that the kinetic energy here is different than the kinetic energy there. No, it's the same. but there are fewer particles up there, so you get a gradient of density. The densities up here are lower than the densities down there. Very good. So this was an interesting exercise in thinking about the consequences of independence in very physical problems. The temperature for a liquid is defined in exactly the same way as the temperature in a solid or in a gas, provided your Hamiltonians are of the form of sums like that, so that positions and momenta are independent of each other. The distribution of temperatures in a gas in the presence of a gravitational field is also independent of height, even though particles slow down. And that's because position and momenta are independent. What I want to do next class is give you yet another really interesting example of how some of these concepts about thinking about probability in this very systematic way is going to be helpful to us. I'm going to tackle quantum mechanics and the double slit experiment. See you next class.